Hi everyone, in this video I want to use the linear optimization problem to solving the transportation problem. So it's a very popular example because if you think about transportation problem are related to the starting point and the ending point, so origin and destination. Although here we're focusing more on the shipping related problem, you can also translate this problem to like a for instance, arranging the flight, the pilot. So that's one of the consulting work I done before for private jet. So they try to optimizing the pilot location, as they know they fly. Let's say they fly out of Erie, they going to, let's say, DC. So ideally they will have another needs from DC to somewhere else. Otherwise, the pilot needs to take some other flight to go into the next stop and then drive the private jet. So how can we optimize this process? So this here have the similar problem. We're looking at shipping the product from one place to the other places and try to optimize in the situation so that they can reducing the cost. So we're using this hypothetical situation so to relatively simplify, but the idea would be very similar. Okay, so Foster generator operate a plant in Cleveland, Ohio, Bradford, Indiana, and then York, Pennsylvania. Production capacity over the next 3 month planning period for one type of the generator are as follows. So as you notice that the 3 months capacity for Cleveland is 5,000, Bradford 6,000, York is 2,500. So total capacity is 13,500 units. So the firm distributed its generator through 4 regional distribution centers located in Boston, Massachusetts, Chicago, Illinois, St. Louis, Missouri, and Lexington, Kentucky. The 3 months forecast of the demand for the distribution center is as follows. So the Boston need 6,000, Chicago need 4,000, St. Louis need 2,000, Lexington need 1,500. So you see that the ideally is where you need it, you produce, but unfortunately it's not the case. We try to specialize, so we usually producing the things at a place where it have low cost. So therefore, so for instance, the Boston needed 6,000, although I think the Pennsylvania might be the closest state, but if you look at York only producing 2,500, so therefore you might not be able to, even you ask all the Pennsylvanias to ship to Boston, it still doesn't meet in the needs, right? So therefore, we need to figure out, given those are the where they produce and those are the needs, how can we optimizing, minimizing the cost so that we can sending the unit to the needed center. Okay, so management would like to determine how much of its production should be shipped from each plant to each distribution center. Figures show graphic of the 12 distribution route Foster can use. Such a graph is called network. Okay, so this is called network. The circle are referred to as nodes, and the line connection, the nodes are arcs. Each origin and each destination is represented by a node, and each possible shipping route is represented by an arc. The amount of the supply is written next to each origin node, and the amount of the demand is written next to each destination node. The goods shipped from the origin to the destination represent the flow in the network. Note that direction of the flow from origin to destination is indicated by the arrow. So to make our thought more clear, so obviously we like to use this kind of called a network chart. As you see this diagram, you can say, okay, so this is where they produce in Cleveland. We can ship to Boston, Chicago, St. Louis, and Lexington, similarly from Bradford. And so for each node, we also label how much they can produce. And for each destination, we also list how much they need it. And then also the arrow itself is helping us to understand which is the origin, which is the destination. And also on each branch, there's some numbers. So let's talk about the number on it, 3276. What are they? So they are actually the cost. So for Foster transportation problem, the objective is to determine the route to be used and the quantity to be shipped via each route that will provide the minimum total transportation cost. The cost for each unit shipped on each route is given in table below and is shown on each arc in the figure above. Okay. So for this problem, we try to help the manager of the company to understand what is the number of units shipped from each origin to each destination so that Foster can minimize the total transportation cost. Okay, so the objective is minimize. So we try to minimize the cost. And can you find alternative optimal solution? So in this video, we're focusing on set up the problem. In next video, we're focusing on solving the problem. And after the next video, we're going to focus on how can we find alternative optimal solution. Okay, so first, let's define my decision variable. So what are the decision variables? So actually the decision variable here is more complicated than you think. Okay, so let me go back to the problem. So basically each branch here will be one of my decision variable. How many we need to ship from Cleveland to Boston, Cleveland to Chicago, Cleveland to St. Louis, to Cleveland to Langston. Bradford to Boston, Bradford to Chicago, Bradford to St. Louis, Bradford to Lexington. York to Boston, York to Chicago, York to St. Louis, York to Lexington. So if you look at the situation here, we total are having 9 possible choices that we need to make, right? How many you ship from one of them. Correspondingly, it mapping to 9 different kind of costs. Okay, 9 different costs. So here, instead of using the notation I introduced before, you can see CB, CC, CS, CL, BB, BC, BS, BL, YB, YC, YS, YL. So you can use this way, or the other way, use X. So X11, X12, X13, X14. So basically, we're using the first subscript to representing the origin, and the second subscript representing the destination. So we can use both way. Okay, so let's see. So the first, what I will do is we can call it CB, Cleveland to Boston. It's equal to X1, X11. So this is representing the unit ship, the number of units shipped from Cleveland to Boston, right? You can see C equal to X12, and this is the number of units shipped from Cleveland to Chicago, and then CS X13, this is number of units shipped from Cleveland to St. Louis, CL X14. This is so this will be the number of units shipped from Cleveland to Lexington. Okay, now to BB X21, right? This is Bradford's number 2, that's the origin, 1 is destination, and then so that will be the number of units shipped from Bedford to Boston. Okay, next one is BC. So this is X22. So let me just do a quick. So in here will be the number of the Bradford to Cleveland. So the next one is BC, BS, and the X23, and then Boston to Bradford to L, X24. Okay, so this first is, so we have a lot. We have totally 9, or no, 12 actually. So here should be the Bradford. So we have 12. Okay, so the next, starting from York, YB X31. So that would be the first. So this is from York, okay, to Boston, and then the YC Chicago X32, Lexington to St. Louis X433, York to L, Lexington X34. Okay, so then we will have the second one here. I'm just trying to go fast. Okay, Boston, Chicago, 3, St. Louis, and Lexington. Okay, but they are from York. Okay, after that, so those are my choice variables. That's a lot. Very good. And then the next is my objective function. As we just reading the case, we try to minimize the cost, right? So that is the objective function as we read the case. Okay, so the case is try to the cost, okay, the determine the route to be used, quantity shipped will be minimize the total transportation cost. So now we're gonna look at transportation cost. So if X11 representing how many we're gonna ship from Cleveland to Boston, so per unit cost 3, so that would be X11 times 3. That gives us total cost from Cleveland ship to Boston. And then Cleveland to Chicago is 2 per unit, 2 times X12, and then 7 times X13, 6 times X14, right? So that's how we just adding all of them together. It will give us the total cost, and we'll try to minimize that cost. So therefore, we try to minimize the cost equal to, okay, 3 times X11 plus 2 times X12 plus 7 times X13 plus, again, I'm already type it because 3276, right? 3276 is the first from the Cleveland to the 4 destination. Bradford is 6523 to the 4 destination. York is 2345. Okay, so those are the number we need to multiply by that specific choice variable. Okay, so X3 and then plus 6 times X14 plus 6 times X21 plus 5 times X22 plus 2 times X23 plus 3 times X24 plus 2 times X31 plus 5 times X32 plus 4 times X33. Last one, 5 times X34. Okay, you can double check if all the cost number matched. Okay, you can go back to look at those numbers. 2, 3, 4, 5, right? Oh, here should be double check. Oh, actually here is a typo. So here should be 5. It's 2545. So there is a typo on the chart here. It's 2545. Okay, but here's 5. Right, 2545. 6526. 6526. Wait. 4. Wait, what is the 4 here? 652. Oh, 6523. Yeah, 6523. Yep. 3276. 3276. Okay, so this is my objective function. Okay, my constraint. Okay, for the constraints has to be going back to the original table here, right? So we're talking about this is how much they can produce, this is how much they needed, so those has to be meet the constraint. Okay, so basically everything coming out of the Cleveland has adding them together equal to shoot smaller and equal to 5,000, and then everything getting to Boston has to be equal to 6,000, right? And 4,000, 2,000, and then 1,500, so etc. Okay, so let's list all the capacity together. So first, everything coming from Cleveland. So the reason I like the notation is because Cleveland is the origin, basically is the first origin. So every subscript is 1 means they are coming from Cleveland. So therefore x11, x12, x13, x14 together, add all of them together has to be smaller than 5,000. Okay, so this is the Cleveland constraint. So it will be x11 plus x12 plus x13 plus x14 has to be smaller and equal to then the production, right? And the next production facility is at the Bedford. Similarly, x21 plus x22 plus x23 plus x24. This one also has to be smaller and equal to the capacity, which is the capacity is 6,000. And then the last is Yorktown capacity. Yorktown had the capacity is x31 plus x32 plus x33 plus x34. This one has to be smaller and equal to the capacity, which is 2,500. Okay, so this is about the origin and then the destination. So the first destination is Boston. So the Boston require us, so everything ending in 1, okay, x11, x21, x31, so they're all sending to Boston. So that one has to equal to 6,000, okay, it has to equal to 6,000 because that's the need. So they have to meeting the demand, 6,000 as the demand. So basically here will be x11 plus x21 plus x31 plus x, sorry, only had 3. This one has to equal to the demand, which is 6,000. And the next one is Boston, Chicago. So everything, the second subscript is 2, x12, x12 plus x22 plus x32. This one has to equal to the demand. The demand is 4,000. The next one is St. Louis. Has a demand, so x13 plus x23 plus x33. So this one has to equal to 2,000 as the demand. So the last station is the Lexington. Their demand is x14 plus x24 plus x34. This one has to equal to the demand 1,500, and of course non-negativity. So x all the x has to be larger than equal to 0. Okay, now those are my constraints. So totally we have 1, 2, 3, 4, 5, 6, 7. 7 constraints besides the non-negativity constraint. Okay, so in my next video, I will show you how we can use the solver to solve this very complicated problem.